And now let's begin to work with the state. Let's begin to derive some interesting relations and properties of such a state. In the first step, let's look a bit more closely at this partition function, and more specifically the log of this partition function. Remember, the partition function is a function of the lambdas, the Lagrange parameters, and the psi. So one thing we can do is we can consider partial derivatives of the log of the partition function with respect to either the lambdas or the psi. Let's start with the lambda. So we have partition function as a function of the lambdas and psi. And now I take the partial derivative with respect to one of the lambdas, keeping all the other lambdas fixed and also keeping psi fixed. First of all, this is 1 over z, and then dz over d lambda I. Let's remember what the z is. So this is d over d lambda, and then we have the trace exponential e to the minus lambda j aj. So the 1 over z stays, the trace stays, and then derivative of an exponential is the exponential times the inner derivative of the exponent. Now this picks out, the exponent is a sum, and we take the partial derivative with respect to one specific lambda, and only the summand that contains the specific lambda will contribute to the inner derivative, and that gives then minus ai. Now you have to be a bit more careful when the AIs don't commute. Then it's when you take the derivative of an exponential, and in the exponential you have several observables that don't commute with each other, then the expression is a bit more complicated, and it's not just the exponential times the inner derivative of the exponent, but it's a more complicated expression. But then when you trace over it, this complication disappears and you're back to this expression. So I encourage you to check that for yourself, but I can assure you that you will get the same result even for non-commuting observables, as long as you take the trace afterwards. But now when you look at this expression here, you recognize 1 over z times the exponential. This is once again our density matrix. So in fact what we have here is the trace of rho times minus ai. And this is nothing but minus the expectation value of ai. So it's in fact very simple. When you're given the partition function as a function of the Lagrange parameters in psi, you can take the partial derivative with respect to lambda of the log, and then you obtain from that minus the expectation value of ai. That's a very simple basic relation. Next, we can look at the partial derivative of the log with respect to the control parameter psi. Same logic, 1 over z, partial with respect to psi of z, but z in turn is the trace, e to the minus lambda j aj, where now the aj depends on psi. And then same logic as before, the derivative of an exponential, that's the exponential times the inner derivative of the exponent. And in this case, this looks as follows. Once again, you have a minus sign. Once again, afterwards, you have the 1 over z times the exponential, which you identify again as rho. So you have a trace rho times the inner derivative of the exponent, which is nothing but the expectation value of the inner derivative of the exponent. And this is, in this case, minus the sum over j lambda j, and then, which you can take in front of the expectation value because it's a number, and then you have the expectation value of the partial of a j of psi with respect to psi, expectation value. And again, the warning, it's a bit slightly tricky when you have non-commuting observables, and also when this partial derivative of a with respect to psi doesn't commute with a itself. But again, the trace heals all of that, and it still holds. So we have two first interesting relations. Let's move on to the entropy. When you evaluate the entropy of your general Gibbs state, and in order to get rid of the Boltzmann constant, I would like to divide the entropy by k, so I no longer have the Boltzmann constant on the right-hand side. This is as before, that's minus trace rho log rho. This is, of course, always true. And when you insert the general Gibbs state from before, then you have a structure very similar to the one that we saw for the Boltzmann Gibbs state already. You have the log of the partition function plus, now in the Boltzmann Gibbs case, we had then beta times the expectation value of the Hamiltonian. And here in the general case, we have the sum over all I, Lagrange parameter lambda I times the expectation value of AI. This is the generalization. Now we can look at the differential. So I take the total differential of this entropy, S over K. And we have several contributions. Let me divide it like this. So this means we have the total differential of log z, and then we have sum over I, and the total differential of lambda I expectation value of AI. By product rule, we can divide this into two parts. We have lambda I differential AI, and then we have expectation value AI times differential d lambda I. What is the total differential of the log of the partition function? Here we can use the results from the previous page. We can write this as the log of the partition function depends on the Lagrange parameters and the control parameter. So we have sum of I partial with respect to lambda I of log z times d lambda I, and then we have partial with respect to the control parameter of log z times d psi. From the previous page, we know that this partial derivative of log z with respect to lambda, this is minus the expectation value of ai. So this is equal to minus expectation value of ai d lambda I, and the rest I leave for the moment, plus d over d psi log z d psi. Now let's combine these two terms with the others that still remain. And you see that this term here, sum of I, ai, expectation value d lambda I, it has a minus sign in front, and it cancels with that term. It has the same structure but has a plus sign in front. So overall, you find that the differential of S over K, that this is equal to sum of I lambda I d ai, expectation value, plus d over d psi log z d psi. Yeah? So this is the total differential of the entropy. Now the total differential of the entropy is now a linear combination of d ai, expectation value, and d psi. This means that the entropy must be a function of the expectation values of ai and of psi. These are the so-called natural variables of the entropy. Now since the entropy differential can be written, appears as a linear combination of differentials of the ai expectation values and of the control parameter psi, this indicates that the ai and the psi are the natural variables of S. The lambda, the coefficient in front of the dai, this must obviously be then the partial derivative of S with respect to ai, keeping all the other ai's and the psi fixed. So keeping all other natural variables fixed. And what's in front of the d psi, this here, this must be the partial derivative of the entropy of S over K. Sorry, it's all S over K. This must be the partial derivative of S over K with respect to psi, keeping all other natural variables fixed. Compare this to the case of log of the partition function. So let me go back for a minute to the previous page. We can summarize these findings and write the differential of log z as partial with respect to lambda times d lambda. The partial with respect to lambda is minus the expectation value of ai d lambda I, and then we have to sum over all I, plus partial of log z with respect to psi times d psi. And to avoid this more complicated expression, I just write it like this, d psi. So again, you, just as in the case of the entropy, you recognize that here the lambdas and the psi are the natural variables, in this case of log z. This is, well, this we had known before. The way the partition function was defined, it's a function of the lambdas and psi, but you also recognize that, of course, here when you write down the total differential of the log of the partition function, it's a linear combination of d lambda and d psi. So these are the natural variables of log z. And what you have in front, so in this case here the minus ai, this is d over d lambda I log z, keeping all other natural variables fixed. And the same here. This is, of course, also keeping all other natural variables fixed. This is d log z over d psi. And so you see you have a comparable structure here for the total differential of the log of the partition function. And on the next page for the differential of the entropy. The difference is, in the first case, the natural variables are lambda and psi, whereas here, for the entropy, the natural variables are the expectation values and psi. Now, there's a wonderful way to summarize these findings in a single figure, in a single graph. And this is called the Guggenheim square. It has nothing to do with the Guggenheim Museum. I can't tell you much about Mr. Guggenheim, this Guggenheim, but it's named after him. And it's a scheme that in a very compact fashion summarizes all the relations that we had on the previous 2 pages. This Guggenheim square has in the top left corner the log of the partition function. In the top right corner, it has the entropy divided by the Boltzmann constant. Then there are 2 arrows like a coordinate system. And then we have the control parameter xi. We have the Lagrange parameters lambda I. We have the expectation values ai. Okay, what does that scheme tell us? The arrows, they have at the tail of an arrow you have a minus, and at the top of an arrow you have a plus. And the same here, you have a plus. The minus of this vertical arrow doesn't matter. We won't need that. The first information we get from this Guggenheim square is that each corner has the adjacent sides as its natural variables. So, log z has as its natural variables xi and lambda. So a corner has the adjacent sides as its natural variables. So this is what this means. This is the first piece of information that you can extract from this scheme. And likewise, the entropy has as its natural variables xi and the expectation values. Now, let's consider the case of log z. It has as its variables, it's a function of xi and of the lambdas. Then you can consider partial derivatives with respect to these natural variables. When I take the partial derivative of log z with respect to the natural variable lambda, then what happens is that I move along the arrow to the opposite end of the arrow. So taking the partial derivative of log z with respect to lambda leads me to the other end of the arrow. So it leads me from lambda to the expectation value ai, with a minus sign because the lambda is at the tail of the arrow where there is a minus sign. That's why you get a minus sign. Maybe for didactical purposes I should have drawn this later, and I should have said when you take the partial derivative of log z with respect to lambda, then voila, you move along this arrow from the left to the right. And because you start at the tail of the arrow, lambda is at the tail of the arrow, the tail has a negative sign, you obtain minus the expectation value of ai. So let me write this down in words. So partial derivative of a corner with respect to an adjacent side leads to the opposite side up to a sign which is minus if at tail, or plus if at top of an arrow. You can check that this works also the other way around. Let's take the top right corner. Let's take the entropy, S over K. It's a function of xi and of the expectation values. Let's take the partial derivative with respect to an expectation value. This leads to the opposite side. This leads to the opposite end of the arrow, and hence it leads to lambda. So the partial derivative of entropy with respect to AI gives lambda. And since we start at the top of the arrow, there's a plus sign. Let's check whether this is true. Let's go back to the previous page where we had the entropy differential. Let's look at the last line. We identified lambda equals the partial derivative of S over K with respect to the expectation value AI with a positive sign. So it works. Furthermore, there's even more in this diagram. You can move from the top left corner to the top right corner. When you do that, you move along this arrow. And when you move along this arrow, you have to add the product of the two ends of the arrow. So, moving along the arrow means that you have to add the product of the opposite sides. So, going from log of the partition function to entropy over K, this means you move along the arrow, and this means you have to add the product of lambda I and expectation value AI. And indeed, let's go back to the previous page again. Now look at the first row here. We have S over K is equal to the log of the partition function plus sum over I, lambda I, expectation value AI. So indeed, going from log Z to entropy, S over K, means you have to add the sum over I, lambda I, AI. And this information is also encoded in the Guggenheim square. This is just the first of many Guggenheim squares that I'm going to show you in the course of this semester. I love these Guggenheim squares because I love compact notation and I love ways of compressing information in a minimal space. This Guggenheim squared is sort of incomplete because at the lower end there's not much that I can write. Just one thing I want to add is that, and I do this in a schematic form, I write here the partial with respect to psi of dot, 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 meaning that it doesn't matter whether, you obtain this lower end of this vertical arrow. You can obtain that in two ways, either by taking the partial derivative of the log of the partition function with respect to psi, and then you go down the arrow. You can also start from the top right corner. You take the entropy over K, take the partial derivative with respect to psi, keeping the other natural variables fixed, and then you also move down this arrow. In both cases, you get the same result. That's what this says. Yeah? And once again, and one last time, look at the previous page. Last row to the right, you see in red the partial derivative of S over K with respect to psi, keeping the other natural variables of entropy fixed, is the same as the partial derivative of the log of the partition function with respect to psi, keeping the natural variables of the partition function fixed. So these two partial derivatives with respect to psi give the same result. The difference is that in one case you keep the lambdas fixed, in the other case you keep the a's fixed. And this information too is encoded in this Guggenheim square. The two opposite sides in the Guggenheim square are called conjugate to each other. So here you have the Lagrange parameter on the left-hand side, and you have the expectation value, or values on the right-hand side, and they are said to be conjugate to each other. And we learned that if, for example, you take the partial derivative of the log of the partition function with respect to lambda, with respect to its natural variable lambda, then you end up to a sign on the other side of the square, which are the expectation values. So by taking the partial derivative with respect to a variable, you arrive at its conjugate variable. And likewise, you take the entropy, it has the natural variables psi and the expectation values. You take the partial derivative with respect to an expectation value, and then you arrive at the opposite side, the Lagrange parameter, and hence you arrive at the conjugate of the variable with respect to which you took the partial derivative. Up to this point, this is all formulated in a general fashion. The lambdas and the AIs, they can be arbitrary. We have an arbitrary set of relevant observables. Of course, in practice, there are some observables that appear as relevant observables over and over again. And I would like to draw up a little list of the most common thermodynamic variables that appear in practical applications. So let's consider the entropy. The entropy has as its natural variables either the control parameters, the psi, or the expectation values. These are the natural variables of entropy. Now let me be very general and let me denote a natural variable of the entropy by x. And it doesn't matter whether the x is an expectation value, or whether it's a control parameter, or whether it's even a sharp constraint. If I have, for example, the particle number given as a sharp constraint, then I work in n particle Hilbert space, and I calculate the entropy in n particle of the density matrix in n particle Hilbert space. Then of course the entropy will carry a dependence also on the particle number. So the x, the natural variable of the entropy, could also be a type 2 constraint, could be, for example, the particle number. Yeah, so x can be of any type. And then you can calculate the conjugate of a given natural variable with respect to the entropy by taking the partial derivative of s over k with respect to x while keeping all other natural variables fixed. So to make it specific, let's start with the energy. We said that the energy is basically always part of your set of thermodynamic variables, a part of your relevant observables. So you have the internal energy, U. Now it doesn't matter whether U is given as an expectation value or whether it's given as a sharp constraint. In either case, energy is amongst the natural variables of the entropy. What happens when you take then the partial derivative of entropy with respect to internal energy? You obtain the conjugate, and we called this conjugate beta. We don't know precisely yet what this beta means and how we can relate it to physical quantities that we know. That will come very soon. but we called it beta. Let me remind you, when we had the Boltzmann-Gibbs state, then you see in the exponent the Lagrange parameter associated with the Hamilton operator, that we call that beta. Again, we have yet to explore what the beta means physically, but we call that beta. And we also know that if the energy is given as an expectation value, you take the partial derivative of the entropy with respect to an expectation value, you get its conjugate, which is the associated Lagrange parameter. Here the associated Lagrange parameter is called beta. So if we take the partial of entropy with respect to energy, expectation value, we obtain beta. And this holds generally regardless of whether the energy is given as an expectation value or as a sharp constraint. Its conjugate with respect to the entropy is called beta. Another variable that the entropy very often depends on is the particle number, capital N. Again, it can be either a sharp constraint or it can be an expectation value. And the associated conjugate, its conjugate, is for historical reasons called minus alpha. And again, very soon we will find out what the alpha means, how we can interpret that. These are so far only conventions, how the conjugates are called. We'll come back to this table very soon. We'll complete the table and also talk about the physical interpretation of these quantities. But before doing so, I would like to talk a little bit more about the energy, because the energy is also a very fundamental concept here. It virtually always appears amongst the thermodynamic variables as a natural variable of the entropy. So we should have a closer look at the energy. So we start from the observation that the macroscopic data, practically they always contain information about energy, either as a sharp constraint when the system is isolated, or in the form of an expectation value. So this means that U, the energy, the internal energy, is always amongst the natural variables of entropy. This implies when we write the differential of entropy, we can always write sort of the contribution from the energy explicitly. We can always write this is beta times du. So beta, that's the partial derivative of entropy with respect to energy, keeping all the other natural variables fixed. And by definition, this is beta. So we always have the structure, this is beta times du, plus, and then we have all the other natural variables, which are not specified, other natural variables, where we have contributions of the form partial of the entropy with respect to x dx. And dx, as I said, they may be of the type expectation value, they may be of the type control parameter, or they may also be of the type macroscopic value, like the particle number given as a sharp constraint. So this is not specified. But this is the general structure of the entropy differential when the energy is amongst the natural variables. We can solve that for du. And then we find that du is equal to 1 over k beta ds plus sum over all the other natural variables, and then we have minus 1 over beta partial of the entropy with respect to x dx. The first thing we notice is that now the energy differential is a linear combination of the entropy differential ds and the dx. So from this we can conclude in the same way that we concluded that for the entropy and for the log of the partition function, that S and X are the natural variables of the energy. Furthermore, we conclude again in the same logic as before, that the coefficient in front of the ds, this must be equal to the partial derivative of u with respect to entropy, while keeping all the other natural variables, which are the x's, fixed. And likewise, this expression here in front of the dx, this must be equal to the partial of u with respect to x, while keeping all other natural variables fixed. So with respect to the energy, entropy S and the x's are the natural variables, and these partial derivatives, so the coefficients in front of the differentials, are the conjugates of these natural variables. Now this will help us identify the physical meaning of the various conjugates, because the energy differential is more familiar to us than the entropy differential. So let's look at conjugate pairs with respect to the energy. So we have here some natural variable of energy. Let me again call that x. And we have then the conjugate of that variable with respect to energy. And we obtain the conjugate by taking the partial of the energy with respect to x, while keeping all other natural variables fixed. You notice that the notion of conjugate is always relative to a certain quantity. So we have conjugate with respect to energy. This means that if the energy depends on a variable x, then the conjugate of x with respect to energy is the partial derivative of the energy with respect to x. We also have a conjugate with respect to entropy. So if the entropy depends on x, and then the conjugate of x with respect to entropy is the partial derivative of entropy with respect to x. So the notion of conjugacy is always relative to the quantity of which we take the partial derivative. So what did we learn about the energy? The energy has as one of its natural variables always the entropy. Yeah? So while in the case of entropy, this has as a natural variable always the energy. When we solve for the energy, then we find that the energy always has as a natural variable the entropy. What is the conjugate of entropy with respect to energy? To find that out, go back to the previous page, look at the entropy differential. We have du is equal to some coefficient times ds. What's in front of the ds? That's the conjugate of entropy. Yeah, that's the partial du over ds. Now, you know from your introductory lectures on thermodynamics that the energy differential has the form du is equal to T ds, where T is the temperature. So what you have in front of the entropy, this is by definition the temperature. So in our table, we can write that the conjugate of entropy with respect to energy is the temperature. This is how in this more theoretical framework we introduce the temperature. What else can we have? For the rest, the energy has the same natural variables as the entropy. It has the same, since in the energy differential you have then the same dx that you have also in the entropy differential. This means that energy and entropy share the same natural variables. So we have a similar list. We have also the particle number n. So imagine in your energy differential you have a contribution du, change of energy, is equal to some coefficient times dn. What is the meaning of that coefficient? This coefficient physically means by which amount of energy you change the internal energy of your system when you add one particle. Now this energy that is associated with adding one particle is known as the chemical potential. And it is denoted by the Greek letter mu. Another natural variable that both entropy and energy often depend on is the volume. The volume is typically of the type external control parameter. You have a system in a container and you can vary the volume of this container. It's something that you control externally. Now look at again at the energy differential. You have a contribution du is equal to some coefficient times dV, d volume. Now, quite generally, what's the sign of this coefficient? Imagine a gas in a container. You have to perform work on the system in order to compress the gas. So it requires mechanical work to compress the gas. And when you do that, you increase the internal energy of the gas. So the change of volume is negative when you compress, dV is negative, but the change in internal energy is positive. You add energy to the system, so du is positive. This means that the coefficient in front of the dV must be negative. And what is the magnitude of this coefficient? It's the pressure. The amount of work that you have to perform to compress the system is minus pressure times delta volume. And this means that the conjugate of volume with respect to energy is minus the pressure. Take note here of the negative sign. This is because dV, when you have a negative dV, then you perform work, mechanical work, to compress the system. By doing so, you add energy to the system, you increase the internal energy, you add energy, and this means that du is then positive. So this is why there is a negative sign. Finally, let me add one more variable that will appear in our first practical example, and that is an external magnetic field. This is of the type external field, i.e. control parameter. Now, what is the conjugate with respect to energy of B? Let me try to add here a little motivation. A very simple Hamiltonian that you can imagine, that we will also soon use in an example, that takes into account interaction with an external magnetic field. The simplest Hamiltonian that you can imagine has the form minus external field times operator of the magnetic moment. The internal energy is obviously the expectation value of the Hamiltonian. Now consider the differential of internal energy. Well, internal energy is expectation value of the Hamiltonian. The Hamiltonian carries an explicit dependence on B. So when you vary B, the internal energy varies by expectation value of the partial derivative of the Hamiltonian with respect to B times dB. But when you take the simple form of the Hamiltonian that I wrote down above, minus B times M, then this is equal to minus the expectation value of M times dB. And you recognize that the coefficient in front of the dB is minus the magnetic moment, minus the expectation value of the magnetic moment. So this shall serve as a motivation why, in fact, in general, the conjugate of a magnetic field with respect to energy is minus the magnetic moment. And here's the motivation for that. So here we have a list of conjugates of natural variables of energy and their conjugates with respect to energy. This list helps us to complete the corresponding list for the entropy. So here's the list that we had obtained so far, and let's now complete this list and also find out the physical meaning of the alpha and beta that we have already introduced. Let's start with the beta. To this purpose, let's go back to the energy differential. You see the coefficient in front of the ds. We said this is the temperature. That's what we define as our temperature. But what's in front of the ds, it's also equal to 1 over k beta. So there's a relationship between T, temperature, and beta. We can solve that for beta, and we find that beta is equal to 1 over kt. So the physical meaning of beta is that it is the inverse temperature. Next, let us look at the alpha. And again, let us have a look at the energy differential. Now, the particle number n is one of the x's that appear. So it's amongst the other natural variables x. What you can see from this energy differential, from this formula, is that the conjugate of x with respect to energy, so that's the coefficient here in front of the dx, is related to the conjugate of x with respect to entropy. That's this partial derivative ds over k over dx, simply by a factor minus 1 over beta. So the two conjugates are related by a factor minus 1 over beta. So if you are given the conjugate with respect to energy, the du over dx, and we have that in our list, then you can calculate from that the ds over dx, so the conjugate with respect to entropy, simply by multiplying with minus beta. Now for the particle number, the conjugate with respect to energy was the chemical potential mu. This implies that the conjugate with respect to entropy will be minus beta mu. So this must be equal to minus beta mu. In other words, the alpha is the same as in the product of inverse temperature and chemical potential. This is sort of less intuitive to grasp, less intuitive than the chemical potential. And in fact, in many applications, we will work only with the chemical potential, but you can just as well work with the alpha. Well, then let's look at the two other natural variables that we had considered in the case of energy, namely the volume V and the magnetic field B. The conjugate of volume with respect to energy was minus the pressure. The conjugate with respect to entropy is minus beta times that. So this gives beta times the pressure. And in the case of the magnetic field, the conjugate with respect to energy was minus magnetization, and with respect to entropy, it is plus beta times magnetization. No? But just as a reminder, what we used here for the last three natural variables, so for the natural variables different from the internal energy, we used the fact that the conjugate with respect to entropy, keeping all others fixed, equals minus beta times the conjugate with respect to energy. That's what we used for the last three entries.